So we've been using area a little bit as not our main thing, but we've been calculating it and relating it to trig. But I wanted to go back and make sure we really carefully justify some of the basics. In particular, the area of a rectangle, a parallelogram, and a triangle. So I've got a parallelogram set up here. Well, let me just say area of a rectangle. We're going to assume that that's known. It's just length times width, or usually we want to write that as base times height. And the base is going to be some sort of width on the page. The height is obviously going to be the perpendicular to that. And we're going to assume that that's absolutely the basics. But a parallelogram, it turns out, is extremely similar, even though it's slanty. And so I want to show you that. I think you've likely seen it before, but if you haven't, it's just a very pretty thing. And it's an example of how you figure out area formulas. You basically do a lot of cutting, or sometimes just a little cutting and pasting. So I've got this parallelogram here, and in fact, I can give you a whole bunch of different parallelograms. And I claim if I move this so that the top line has the same height above the bottom line, and that height is the h there. It's the perpendicular distance between two lines. I claim I'm not making that parallelogram bigger or smaller. I claim all of these have exactly the same area, and therefore the same as the rectangle with that base and that height. So one way to do that is just pick one of those parallelograms, and I'm going to show you how I could do just a tiny bit of cutting and pasting and turn it into a rectangle with the same base and the same height. So now I've colored it to show that I'm going to think of this right-hand triangle as special. I've dropped altitudes from A to the line of the top and from G to the base here. And now I've got a little slider that just lets me slide that triangle. And of course, if I cut it out and I slide it, I'm not changing its area. And then I'm just going to paste it back in on the other side. And it fits perfectly, of course, because this is a parallelogram. The side BE and the side AD are parallel. And certainly these two verticals that I've drawn are parallel. Those are congruent triangles, and it just slides into place. And so the area of the original parallelogram is just the area of this rectangle, and that's base times height. So the punchline there is beautiful. It's just the same exact formula. You just have to make sure, be careful that height here is not the length of the slanted side. The other thing is that just as we've been looking at a little bit for triangle areas, and we're going to get more into, specialize on that, you have to choose a base first. And I'll show you an example of that in a second. Choose a base first. Then the height is relative to that. It's the length of an altitude. So in this example, we had one side horizontal, so it's natural to call that the base. And then the height was the length of either one of these perpendiculars that connects those two parallel sides. It was not the length of AD. So now I've put in two numbers. If h equals 12 and b equals 5, just kidding, b equals 12, getting ahead of myself, and h equals 5, then the area is going to be 60. Very, very simple, as long as you know that h. And then we might need to do some trig sometimes to figure that out. We got right triangles in here after all, but right now we're not going to worry about it. So the next thing I want to show you is how you can go from here, from a parallelogram to a triangle. That's very beautiful as well. So now what I've done is I've drawn a triangle inside this parallelogram by just connecting, by making a diagonal, connecting two of the corners. And I've got that shaded in on the upper left. And what I'm going to show you is just by rotating that, I'm going to create the other half of parallelogram. So I'm rotating that. Now I'm going to leave that purple copy in place. Unlike cutting and pasting like I did before, I'm going to leave that purple copy in place and then rotate another copy. And what we see is a triangle. A triangle is half of the parallelogram. So it has half the area. Okay, and let's see. Their bases are the same. Like if I look at the green triangle, I can definitely think of the base of the parallelogram as a base of the triangle. And I can look at, say, segment GB or segment AF. Those are exactly altitudes. Let's say this is a good one. AF is an altitude of this triangle relative to this base. So if we think of the base as the DE, for example, then AF is exactly what you get if you dropped an altitude to that base. So these, for the parallelogram, have the same bases. This parallelogram and the triangle have the same bases, the same heights. So the area of the triangle is just something we've been familiar with for a little while now, 1/2 times base times height. Okay. So here's one more aspect of this that I mentioned, that when you think about the area of a parallelogram, or go back to parallelograms here for a second. When you think about the area of a parallelogram, you are going to pick a side that you are going to declare to be the base. And then you don't have any choice as to what the height is. It's exactly the distance between that base and the other parallel side opposite. Or in other words, it's the height of dropping an altitude from one of the points on that opposite side back down to your base. And that right angle is absolutely crucial. But somebody else might say, hey, I'm thinking of like this segment MO as my base. There's nothing wrong with that. If you rotated the parallelogram, you could make that horizontal if you wanted, but it doesn't really matter. Well, what would their height be? Their height would be, you look at these parallel bases, MO and then LN, they have the same length. Extend one of them to be a longer line so you can drop an altitude. That looks rather weird, but if you turn your head so that LN and MO look horizontal, it's exactly just how high that is. It's how far apart LN and MO are in terms of lines. So it should be true that you can calculate the area of this in two ways, with base being LM and height being NQ, and we'll do that in a second, but which should be the same answer as base being MO and height being H3. Notice MO is rather smaller as a base than LM, and it certainly looks like this other height that's labeled H3 is rather longer than 2.71, so it's plausible that they might give the same answer. We know they should because they're both legal ways to calculate the area. And so what we can do is we can say, okay, the known base matching that known height, that's the area of the parallelogram. And therefore, that should also equal 3.58 times this mystery height, which happens to be, it wanted to label it as H3 here, okay? And so we can easily solve that. H, well, not a superscript, not H cubed, is going to be 18.022 over 3.58. So this is already something kind of interesting, that if we didn't think about areas, so we got to get just over 5. If we didn't think about areas, this would be a hard problem. You could actually solve it with trig and inverse trig, but it would be much the hard way to do it. But realizing that this picture, both of these dotted lines are exactly what two different people would use as heights to calculate the area of this same parallelogram, and using the fact that we know both the bases, that sometimes is not going to be true. Notice we didn't need the 3.58 to figure out the area. Just this base, the 6.65 and the 2.71 were plenty. But if you also know the other side here, you're going to know this h.